I'm live. Hello. Good evening. Today, we're going to learn about Ohm's law. Welcome to Electric Circuits. My name is Meriwether Remark. I'm an electrical engineer, and I'm here to help you learn circuits. So if you're a student studying circuits to get your degree, you'll run into lots of circuits problems, and we want to be able to do them efficiently. And there are a lot of basics we have to cover. We need to be able to solve this problem, and if we can't, we're in trouble. Let me write this problem down. Where's that? Okay, so here's one circuit problem. And we have I. We have V. So typically you have something like this, and they kind of want you to know, they give you what VG is. This is VG. And they give you what IG is. Or maybe they don't. Well, this time they did. So they give you IG and VG. We have values for them. And they say, we want to know what is R. So this is kind of like a complicated thing if you don't know how any of this stuff works. And, well, they might also ask you for power. What is the power that is delivered by the power source? And now you're like, oh Jesus, what am I doing? What am I gonna do? This is hard. So I remember from my triode stream, I got some feedback about that, and they were like, this is like graduate level stuff. You got to start from the basics. So you know what? We're going to start from the basics. So like I'm going to give you the tools to be able to solve this circuit tonight. So what we would like to know is, how can we find R, the value R, and how can we find the power of R? And the other thing we want to know is that if we like have a value for R, and if we have a value for the P of R, which is the power delivered to R, we would like to know what would be the IG and the VG. Basically, if we know this, we can like know the other values too. But we need to start from square one. So let's just get square one. So now it's like you might have a question, like, what does V mean? What is V? Like, I say V, and you'd be like, what is V? And you know what? Mechanical engineers are required to take circuits as well. They got to know this stuff too. And it's like they don't see. Actually, a lot of people don't see or observe the electrical phenomena that's like happening. Like there's a reason why this model, this right here, is a representation, is essentially a mathematical model of an underlying physical phenomena, and that this is a way to simplify it so that we can work with it and use it and essentially design essentially circuits to solve a customer requirement, or like design requirements to meet a customer need. So one of the issues is that some people might look at this and think like this is some magic pixie fairy dust thing. It's like what is this? What is it? And you know what? I have with me an actual mechanical engineer with me. He's here, and he can talk whenever he will like.
Yeah, I know. I might be an engineer, but I am first and foremost a hobby gardener, and so this stuff is all way over my head.
Yeah. So wouldn't you say that like circuits and the electricity in circuits is some sort of like magic fairy dust? Is that like essentially it's like it's there, but you kind of don't know the machines or why it runs well.
Definitely a black box.
Black box. Okay. So one thing I could tell you, I'm going to tell you something, and it's going to be like a black box. I'm going to tell you a sentence, and it's going to be a complete black box. And that block, and here's his sentence. Here's the sentence. V is voltage, and voltage induces a current of charge through a conductor. See, I bet you didn't understand anything from that sentence. It's like I was enchanting some sort of arcane magic. I mean, am I wrong?
Yeah, when I think current, I think of like a river or like something recent,
Something recent. So okay, hang on. Oh gosh, my character, he's a bit too angled right now. Let me angle him back. There we go. There we go. So okay, so OMG, what is voltage? We need to know what voltage is. So I'm going to tell you. Just put this one right there. So what we want to know is we want to know something, a little phenomenon known as electric potential. So for gravitational potential energy, you know what that is. It's easy. You can see that. We have to put a lot of work to give something potential energy. Potential energy versus kinetic energy. Ideally speaking, that's like a conservative force right there. So, by the way, I'm assuming you guys know at least classical mechanics, physics 1 stuff. So we have to put like a lot of work, or maybe not so much work, maybe not so much effort, or sometimes we have to put a lot of effort to move something to give it a higher gravitational potential energy. So like, this pen, well, now it has more potential, and now it has less. You know that stuff. So roughly speaking, like electric potential, this is the same idea. But we're doing it with charge. So if we can harness that idea, we can like use this idea to basically power our electronics. Because from this circuit, if we ignore this gibberish, essentially this is a power source, and we're powering some kind of we call it a load. This could be essentially an electronic device, like a computer that you're watching this on. So we want to be able to know how that works and why that works. We're starting with the essentials. Now you might say that, but wait, you can see and feel kinetic energy and potential energy. Like you can see kinetic energy and you can see potential energy. But isn't like electric energy some kind of magic pixie fairy dust thing? Like charge being observed from electrons and atoms, like you can't see that. Isn't that just some excuse to like hand wave something we can't see? And also, doesn't your instructor just hand wave some other generalizations and tell you to believe it? And you do believe it because you want to get an A. And you want to see your computer turn on. But you see it turn on, so it must be correct. What your instructor is saying is totally correct, but you don't really understand it, and then you get screwed by a hard problem, and then you don't get an A, and that kind of sucks. So it's been suggested by someone that I know, suggested that you can just make up a brand new vernacular with different monikers. Like instead of calling it current, you could call it like fairy dust or something like that. And you can use this new vernacular to supplant the existing vernacular. And it can like, you can make it make sense. And essentially, the reason why he said this to me was because it was a point to essentially illustrate the inadequacies of instruction. So, I mean, like, hasn't that happened to you? You like go to class and you're like sitting down and you're like, well, I know it's math and I kind of know math. So if I can do that, then I can get my A and I don't care. And the problem there was that like the issue is that this would be like an incredibly hard task because you're essentially like the thing is that I would argue don't like that idea. Just get rid of that idea. We don't need it. You can just use the existing language, the existing monikers, because they still make sense within themselves. And charge, electric charge, is not like you could say that electrical charge isn't like classical mechanics, and you know that's true. But there are a lot of similarities and analogies to classical mechanics. So it's so do you even know what charge is? Like, do you have any clue?
Is it like mana?
Well, I mean, kinda. No, not really. Mana is like a stamina thing, but for another attribute, like spellcasting attributes. But this is different. So with charge,
I get it. So mana is more like voltage then.
No.
Like if a spell costs like 70 mana, that would be the same as it having like a voltage drop of 5 volts.
That's more like intrinsic power for an object or assortment of power sources. You could say that they have mana, but I would like you to like forget the mana part, and I'll show you why. Because you don't need to. It doesn't need to be mana. So now talk about charge is that we have an atom, and we know that there's a center. So we have like you know chemistry. I'm assuming all you guys know chemistry. The center of an atom is it has a bunch of neutrons and protons, and the thing is that the idea is that an atom that is not an ion, like a metal that's not an ion, it has an electron cloud, and then like the amount of electrons in that cloud, it balances out the protons. And I know you understand this. I mean, you at least know chemistry. So
maybe.
Yeah. But you have the idea. Think about magnets. You know how like if you have magnets of opposite forces coming together, then they just stick to each other. But if you have like not enough magnets, say that you have like, I don't know, like 4 N magnets, and you only have like 3 S magnets. Well, in the total idea, you have N plus 1. So you're more biased towards the north of magnets. So if you have like an ion, which an ion is essentially a biased, like it's this idea but biased, because like we're missing a south, so we're biased towards the north. So if you have an atom for a metal and it's like missing an electron, it's missing it's missing an electron, so now it's biased protons, and this is how we're going to call it. That is a proton. Oh wait, the plus should be up here. Don't worry about that. So that is a proton, and if we're missing an electron, this atom is biased plus proton. But so you get that, right?
Yeah, I think I get that. And different metals have different amounts of like electrons in the cloud, right?
Basically, that's the idea. So Let's see. Got some good. I got a lot of notes right here. These notes are amazing notes. I took them all. So yeah. A charged atom is called an ion. So if it has like a plus thing right there, it's an ion. So in the 18th century, we know that if we rub glass with like a silk cloth, we would get a charge one way. And if we rub like amber with a silk cloth or maybe rubber, we would have the opposite charge. And a guy named Benjamin Franklin decided to call one of those positive charge. And I think that was the glass one. So the glass one, the positive one, the lack of electrons, we're going to call that positive. So if you can like transfer, if you can like move electrons one way, like that's an electron, we'll call that an electron. If you can move it like one way, you understand that a positive charge is moving the opposite way. That's kind of like the idea. If it's like going, if you like imagine it going, if you can somehow imagine it going through like some sort of pipe shaft. And we know that there's stronger charge. If we have like a lot of plus, like a big plus, that's more charge. And so if you get like a glass rod and you rub it with a silk cloth, it's going to be quite positively charged. So let's go to the next part. So maybe there is a method to all of this madness. Let me see. How's this doing? We're doing pretty good. The computer's doing pretty good, I think. So there's a method to this. So if we have like there's a reason like we have all this existing mathematics, we have all this existing vernacular that took us like hundreds of years to figure out. Like, don't you think that that there's an underlying reasoning why we have like you know how like you think of it like some sort of like magic kind of thing going on, but all this stuff still makes sense and the math does check out. Like how do you like you know there's something there that makes it work. And one of the ways to like get you to see that is that like to explain electric. Now that we're going from this is how we can see electric potential. I'm about to show you how we can see electric potential. So you know how like there's gravitational force, and how like a big gravitational object has an influence of force on another object, especially if it's really big. Well, with charge is the same way, but you can actually like see it work because like gravitational force for like us is like not big enough to have like a strong influence over something. So this is let's take this out. So we're gonna do this. Force due to charge. Oh, look, we're getting there.
Wait. So can you go back a second? So when the warlocks from like 500 years ago used to like rub amber with a cloth or whatever, or glass with the cloth, they're basically moving the inherent magical potential from one end of the amber to the other.
Well, actually, let me check.
Oh, and that must be how they make their wands. They must move all the potential to the point of it. That kind of makes sense, yeah.
That kind of makes sense. Well, I mean, that's one way to think about it. So, So a not like if like you get that, let's say if you get this. Okay, so here's the deal. Here's the interesting part. Force due to charge. This has to do with force due to charge, answering your question. So if you get like a glass rod, like let's use this thing. If you get like a glass rod and the magic wand and has a bunch of plus charges all over it, and if you get like a balloon, but it's not just any balloon. It's like a balloon that's also a conductor. Like say it has like a layer of like maybe aluminum. So if you have a balloon that has a layer of aluminum on it, what's going to happen is that because the aluminum is a conductor, like the ions, one of the special things about the ions is that they can accept electrons. And then the electrons, it's like due to the structure of an ion and like a conductor, charge can actually move across from it. Now that's a little bit different from a non-conductor, but this is a conductor. That's one of the special things about a conductor. So, so right here, what would happen is you would have the negative charges want to go towards the positive charge, and would have the positive charges will biased away. So it's like if it were like a neutral, now it's suddenly charged one way for the other, and it would want to go towards the magic wand from the warlocks. So yeah, you got the idea.
Interesting. So if I was like, if you replace, well, actually, if instead of like a cloth, instead you used like sandpaper, and then you just scraped off like little glass pieces,
Yeah.
that gravitational energy that you're scraping off the glass pieces upwards is the same thing as the pixie dust that you're bringing up otherwise with the cloth.
What do you mean by the same thing? You mean like the same?
So basically, you're saying a cloth is to these quote unquote charged particles as, sandpaper is to glass pieces.
No. Glass, but if you're using sandpaper, you're physically removing like parts of the glass away. But that's like friction force and destruction of another object to move pieces of it away. That's not really the same thing. You're not destroying a piece of the glass by charging it.
So where does if the warlock's using his magic cloth, where do all like the anti-magic particles go then?
Well, the thing is that they should be on the silk or on your hand.
So in that case, then the sandpaper is going to have the glass pieces on it.
Either that or the floor.
Yeah, and then when the glass falls from the sandpaper to the floor, that is kinetic energy. I see. This makes sense now.
Basically. Well, I don't, the little there. Okay. That's the idea. So, so let's do force due to charge. I'm going to show you force due to charge. So roughly speaking, and a conductor has a small fraction of its electrons not bound to atoms. That's one of the great things about a conductor. And the atoms can like move around in the conductor like on this balloon. So like this is like something called like electric induction.
Wait. Hold the phone.
Okay. What's up?
So you said it was a conductor.
Yes.
Yeah.
Yes.
But I always thought that balloons were made of rubber, and that was supposed to be like an insulator.
No. This balloon has a layer of like aluminum on it, like aluminum plating, so to speak, like very fine, very thin. Like how you have those aluminum sheets when you're in your kitchen. This is like an aluminum balloon. And
it's like Alex Jones with the hat. Yeah, I get it.
Yeah. Where people wear hats with those. Yeah, that stereotype.
Got it. Okay.
Oh Jesus. Okay. So here's what we're doing. Okay. Now, I'm going to show you like this phenomenon right here. You can actually like measure it, or you can like calculate it. So okay. So let's say you have a charge Let's call it charge Q. Q is like charge. So if charge Q, and we have charge Q2. This is Q2. And what we have here is like a distance that separates them. We're going to call it R. Yeah, so this distance like separates both charges. Now, don't forget, we're going to talk about vectors. So like the direction from here to here, we're going to have a direction, R hat. R hat. And the relationship, a man, I think it was, I don't know if he actually found it out, but they named it after him. So there's a force. What we have to know is that there's a force that this charge has on this charge. And it's true. It is true. Like how the magic wand makes the aluminum balloon move back and forth depending on how it's charged. There's a relationship between the charges on the wand and the charges on the balloon. And we can write that relationship as the force on charge 2 due to charge 1. The force on charge 2 due to charge 1 is equal to charge 1, charge 2 times a constant. The way you find this constant is quantum mechanics, and we're not talking about that right now. And the distance r squared. And don't forget, since it's a force, we have a vector. And we're going to call this relationship right here is called Coulomb's law. So this is like when you play those video games and you see how those magic wands do that stuff, but they don't tell you how it works. Well, this is how it works. This is what's happening. And, well, so if the charges are like both positive, like plus charge, like north and north, they're going to like repel. So this right here, if both charges are positive, the force is positive because we already talked about the direction, the R roof of 1 over 2. I mean, not 1 over 2, 1, 2. And that's the same thing right here. So direction, they're both the same direction, both positive charges. It would move the charge that way. Now, if one was negative, then the direction we would have a minus sign there. And so the direction, therefore, is the opposite, which makes sense, which is what happened with the balloon. The balloon, the opposite charges, they want to come together.
Wait, is this like infinite energy then?
What do you mean infinite energy?
So let's say I have a remote control. Okay, a remote control in my living room.
Yes.
And in there I got 2 AA batteries, and they're facing up opposite directions, right?
Yeah.
Radius, R value, let's say a 1 centimeter apart, center to center.
Yeah.
Then so based off this equation, wouldn't like the negative side of 1 push the positive side of 1 infinitely like clockwise? And we could harness that and power the Earth.
Well, the problem there is that, like, it does have a force. You're right. That force does influence that charge, even at a very large distance away, unless that distance is infinity. So until it reaches an infinity distance away, it will experience an influence from that charge. But if you draw a free body diagram, and if you find out why charge isn't moving, it's because there's another influence on that charge. So it could be like the charge might be on an object, and it's bound to that object because of the other charges on that object, and it may not be able to freely move around in free space unless you force it there. So that's an idea. So like, let's see. Wait, whoa, I have an example. So the thing is that I can't charge the Earth. Well, depends on how big the charge is. So,
like a regular AA battery,
regular. No. Actually, towards the end of this stream, I'm going to show you why a AA battery can't actually do that. Like a AA battery has problems.
It's a myth.
Oh, basically. Well, I mean, no, not really.
Now we're on the same page.
Okay. So I want to illustrate to you the difference between like the force of charge. Let's call this, what do I want to call it? The force of the electric force that I just showed you. Let's call it F of E versus the gravitational force. So you remember the formula for gravitational force is mass of 1 plus the mass of 2 plus some gravitational constant plus r squared r roof. Yay, we knew that. So what's the gravitational force for Q? This one and this. What's the gravitational force? So we know that the mass of like are they electrons? Are we going to use electrons or protons? Okay, so let's say that they're protons. Let's say these are positive charges, so they're protons. So we know F of G is equal to the mass of the proton squared times the constant R2. And we know the F of V is the charge squared times a constant. So now let's say if we divide. So by the way, we know that the charge of a proton is equal to 1.6 times 10 to the, I think it's negative, is it 19 or 29? I think it's 19. Negative 19 coulombs. And we also understand the mass of a proton is about 1.67 times 10 to the negative 27, kilograms, yes. So if we know this, and we divide force, the electric force, right here, this one right here, divided by the gravitational force, that one right there. If we divide them, we're going to get about Q constant divided by the mass of proton squared times gravitational force. It's about 1.238 to the 36. So this is much bigger, and that's still not enough to power all the things in the universe. This is page 4. So we can see that the electric force is way stronger than gravitational force. So, like, electric force is very useful, and knowing how charge works is very useful. Don't you agree? Now, what up?
Yeah, but is there more mass or is there more electrons in a AA battery?
Well, here's the thing. If we have like a bigger mass, then maybe that would change this ratio. But if the mass if it's a mass of basically the mass of a proton is like really small. Now, if it was an electron, I think electron has a mass of an electron. Oh, electrons are mass is even smaller. The mass of an electron is even smaller. But if you have bigger objects, you could have bigger FG. But the whole point is that FE is pretty good, And now, one thing that you know that the FG has something to do with how you can calculate, or like the force due to gravity has a lot to do with potential energy, gravitational potential energy. So I want to show you electric potential energy. Is that what it's called? Electrostatic potential energy. See, we're getting close. So electrostatic potential energy. Let's write this down. We're going to call it U. So here's the thing about it. Electrostatic potential energy. So we have two positive charges separated by a distance r. And Q2 is at P, point P. So here's the deal. So we have here a positive charge, Q1, right here, little distance, positive charge Q2 at point P, and this is separated by R. We have R, and now we have these are two positive charges, and we know that the charges are repelling each other. So we need to if we need to bring the charges together, we have to exert an amount of work on, say, this charge right here. So we are pushing the charges together like a spring. I know you understand what a spring is. You know what that is. I don't know what a spring is, but you know what a spring is. So Matthew, when I was trying to understand quantum mechanics again, well, not quantum mechanics, sorry, I meant classical mechanics. I had to basically think about it in terms of electrostatics.
Wow.
Yeah, basically.
I mean, a spring is basically just the physical version of pixie dust. So yeah.
Yeah. So it's so the pixie dust, or the electrical charge, the force due to charge. We understand that we are doing work on this, and we're transferring that work to electrostatic potential energy. It's basically potential energy, but we wrote electrostatic on it to explain the phenomena of charge, two positive charges coming together. So this is electrostatic potential energy. Now we're moving Q2 from a long distance away to this point. So let's try to solve this problem. Let's try to find energy. Let's try to find the amount of energy let's try to find energy. So let's do a free body diagram. Yeah, you know what that is, right? So a free body diagram on that charge. And we have the charge due to, so I'm here. I'm using me. I'm Merriweather. And I'm pushing this charge to this point from a big distance away, a huge distance away. So the force of charge Q1 on me is this Q1 on me. It's a vector. And I am doing my force against it. FMR, Merriweather. So this is the force of charge 1 against me, because I'm bringing the charge to P, the Q2 to P. So one thing we recall is to get work. The work is the line integral of its scalar tangential component along the path of its application point. So from A to B, we have F of S dot ds joules. Well, okay, there's a dot right there. It's kind of above it. I messed up. So we know this. So what's our work? So what's my work? So the work of Merriweather remark from infinity to R, I guess, no, R is this, from here to here. Right here is the distance R. So we're going from infinity to R of Merriweather dot dr. So this integral, I'm not doing this integral. This integral is dumb. So So I'm doing easier integral. So we're going from basically r to infinity, easier integral to do. And we're doing the force that we know. We already know this force. We know this force already because we already did it. You remember that. So F of Q1 on Merriweather, dr, and we know that remember, we know that F of mr is equal to minus F Q1 mr. So we're flipping, we're flipping the integral right here to get rid of that negative sign. So the math checks out. And so if we do the dot product, we know that the angle between F Q1 mr and dr is 0. So we know the dot. We remember dot product, right? You guys remember dot product. So recall that A dot B is equal to A B cosine, and this is 1. So actually this isn't 3. This is 5. That's 5. Pretend that's 5. So this is 6. So we know that work of Merriweather remark is equal to Q1 Q2 4 pi. This is the permittivity of free space. It's like another constant. You know how weird this stuff is, and we have to live with it. So r dr squared, and I'm just going to tell you that the answer. Okay, the answer is Q1 Q2 4 pi epsilon 0 or epsilon naught divided by r and joules. And that's a scalar. So this is like the amount of work we're doing. This is we're going to call this U. So this U is electrostatic potential energy. So now through all this weird stuff in calculus, we know we can calculate energy just like we can calculate potential energy. Like this is it. Like what magic is there? Is this literally pixie dust anymore?
Yeah.
How's it pixie dust?
I mean, just because you write these runes on a paper doesn't mean it's not pixie dust.
These runes. This is calculus.
Yeah. Call it what you want.
Okay. This guy's crazy. This guy's crazy. So, but this is like gravitational potential energy, but like a different way. So and like the thing is that here's the thing. This is electrostatic potential energy. But the next step, in order to understand how we can power electronics, we need to know electric potential. Write that down. Electric potential. So electric potential, not the same as electrostatic potential energy. I just showed you what that is. And come on, Matthew, you know all this stuff. You know this is calculus. And there it is. There it is. It's right there. But that's for like 2 charges, by the way. That's for like 2 charges. Electrostatic potential energy, electrostatic potential. It's not measured in joules. Excuse me. Now, I'm going to show you. I'm going to show you what I'm talking about. So I'm going to do it again. I'm going to do this little problem again. I love doing math. But guys, like reality, I'm just showing you integrals just to show you that the math works out. If you were to like in circuits, we're not going to really go over integrals. Okay, so circuits is like what I'm showing you is like the basics of like EM theory. And circuits is a special case of EM theory. We're not going to be doing a whole lot of integrals and stuff like that in circuits until we get to the Laplace. When we get to the Laplace, there's a lot of integrals there, but wait till that. We'll get that. We'll do that later. So we want to do it. Electric potential. So this is electric potential. Let's say we have some charge Q, big Q, right here, and at some point P, we have a small charge, little q, and you know the shindig, that's R, and we know electrostatic potential energy is equal to Q, big Q, divided by 4 pi epsilon naught R joules. So we know one of the things, the idea is that we have how much energy is being out, but we would like to know is like a very useful way of looking at this is not how much energy is being put out, because we don't want to be able to do this whole thing all over again. To a way we can analyze this as it affects other charges, like if we have like other little charges around here and we want to know what Q is influencing them, well, we can. So if we divide this by charge, we get electric potential. Electric potential is work per unit charge. So that's joules per coulombs. So that would be electric potential. We write it as V, because this is volts. And we're calling it after Volta, or whatever. Voltaire? Yeah, Voltaire. I don't remember the guy. Probably French. And this is it. Joules per coulombs. Now this is volts, and it's a scalar, not a vector. Yay. Is there anything else I want to say? So here's another idea, another way of looking at it. So if we have one charge, Q, we can calculate the electric potential at any point. Yes. See, that's that's a good thing. So if we want to find how much work, if we know electric potential and we want to find the amount of energy, well, we can just multiply it by the charge that we know. See how useful this is? We don't have to do all that integral stuff. We can just multiply it by a constant, and then we have what we need. So if we increase R, say that we increase R. We increase R, like this distance, if they're further away, if R goes up, we understand that the electric potential goes down. Yes. And we also know that if the Q is positive, then we know the electric potential is also positive, because it's pushing it away, because because Q is positive. Now this is like a test charge. We're thinking of it as a test charge. We're always going to use a positive charge for a test charge, and how we think about this. Now if Q is negative, well, then it wants to go the other way. So the electric potential flips. And so if we have the test charge, or the charge, the Q, we create potential because we put a lot of work just to get it there. And wait, someone's calling me? No way. No one's calling me. Good. So if the charge is negative, it wants to go there anyway. Think about this. If test charge is negative, it wants to go to the Q. It wants to go to the positive Q. So if the Q is positive, the test charge, positive test charge wants to go away. If Q is positive but negative test charge, it wants to go towards it. And also if big Q was negative and the test charge was positive, it still wants to go towards it. But if we have negative Q and negative little q, it wants to go away. So like this is, we have to exert a positive amount of work. But for this case right here, well, it's negative work because it wants to go towards it. Like it wants to go into each other. And it's like that's like that's how this is like similar to classical mechanics. Because you get positive work, you got negative work. See, not very pixie fairy dust at all. So, what's confusing? You have a question? You got a question?
Nah, you can keep going.
Okay. Forever hold your peace. Oh wait, I don't want you to see that. So now we understand how we can manipulate charge and move charge. And we want to see if we can like measure how much force there is per charge. So, what I did is I did work per charge, and that's electric potential. So we know how much work we have to do per charge. But what about force per charge? Have you thought about that? Now this is quite necessary to understand how power is delivered to an electronic device like your computer. We have to understand how much force a charge is exerting on another charge or other charges.
Yeah, me personally, I really can't get that much work done per charge on my laptop. Battery dies so quick.
Okay. Yeah, basically. Okay. Here we go. Okay, I'm going to show you this. This is going to be great. This is going to be lovely. What's this? Okay. So, newtons per charge. We call it, electrical engineers call that electric fields. That's what that is. Newtons per charge. And I'm going to show you why newtons per charge makes sense. So, the same old problem. Let's do the same old problem. The Q, and we have the little point right here, and we know the R roof. We know the direction because this is not a scalar quantity. Because force isn't a scalar quantity either. So electric field is not a scalar; it's a vector. So we have the point P, we have little q, and we have a force exerted on little q by big Q. We're going to call that F, and the distance is R between them. So we know the force. Force is equal to little q, big Q times some constant, R squared, R roof. We know that from what we did before, from Coulomb's law. This is the case. And Coulomb was right. Well, actually, I don't know if he was right. They named it after Coulomb in honor of him. So whoever did that person's right. Unless I got my history wrong. So electric fields is simply the electric field. Oh, wait, not that. The electric field of electric field is equal to the force divided by Q. And that would be, boom, newtons per coulomb. Yep. There you go. That's electric field. Now, okay. Electrical engineers. I'm doing this for a reason. Newtons per coulomb. I'm doing that for a reason. We'll get to the volts per meter later, but I'm doing this for a reason. All right? So don't get angry at me. If you want to get angry at me, go somewhere else. So, if now, as an idea, if the charge were negative, if the Q were negative, well, we would have a minus sign, so that affects the direction. So, just so we get our vectors correct. So, one of the things that's important to know is that if we do this around like a charge, so we have a charge right here. If we were to try to measure electric field around a charge, say this is a positive charge, the field vectors would kind of look like this. They kind of look like that. And if it were negative charge, like if we were measuring from the positive perspective, well, they would go into the negative. Does this make sense?
Yep. Crystal clear.
See, he said crystal clear.
As clear as a crystal ball for some kind of, old wise oracle.
Nice.
Powered by pixie dust.
Powered by pixie, which is charge. It is. So now let's do a little example problem. Let's do an example problem. Page 10. So, say that we have a sphere, and the sphere has an even distributed charge on it. Like a sphere. Pretend that's a sphere, and it has a charge evenly distributed on it. So, what's the electric field at any point on, any point in space, basically? We have the center, and we have radius r, and let's say we have some point right here, and maybe the distance between this. Okay, we have some point right here, and the distance between this point and that point could be r. Oh, no, not R, big R. Little r. So, one of the things that we have to understand how to do this problem, we have to borrow something, a solution. And we have to borrow, in order to solve this problem, we have to borrow one of the major laws of electromagnetic theory, and that is Gauss's law. So, how should I say this? To understand how Gauss's law, like the real hardcore math behind it, is a little bit beyond the scope of this, or what I'm trying to do. So we're just going to accept it as true. Like ooga booga, it's true. Maxwell equations. There we go. So this is called Gauss's law. So the flux of the electric field out of an arbitrarily closed surface, like an imaginary, if you like reference it's an integral, we're gonna do an integral. If you imagine it around a closed surface, it is proportional to the electric charge enclosed by that surface. So the flux, like the amount of the electric flux, is like electric field going through a dA, or like a very small surface area, and we call that a dA. That's kind of how we denote it. I'm sure Matthew remembers that. So a closed surface, the little circle means it's a closed surface of the electric field. Dot product over the dA is equivalent to the sum of all the charge divided by the permittivity of free space. I think that's permittivity of free space. So, so to do this, to know the electric field, one of the things we have to know is that the symmetry point inside has the same flux at all points on a hypothetical sphere. So the electric field inside is radially pointing outwards, or it goes inwards depending on, charge. So on the hypothetical surface, the electric field that is with the dA. So think about this. The electric field is like parallel with the dA. So we have like a hypothetical dA on the sphere, like the dA. The electric field is like coming out with the dA. So if we do the dot product, if we do the dot product, the angle between them is 0, or it's pi, depending on which way the electric field's going. So we know from multivariable calculus that the area of a sphere is 4 pi r squared. So we can write it as 4 pi r squared times the quantity of the electric field, like the magnitude, equal to all the charge, which is what we have on the surface, divided by the permittivity of free space. So there is no charge inside the sphere. If we do an imaginary surface, if we do an imaginary r, like a little r inside this point, the center point of the sphere, and we're inside it. There's no charge inside this. So we know from Gauss's law that the electric field is 0. And it's kind of like the way this kind of works, like the reason why it's 0, think about it. All the charge on the sphere, it's like canceling everything else out. It's like the uniformly distributed charges each individually contribute to the E inside the sphere. I mean, the electric field. OBS disconnected for a second. I'm sorry. So, okay, I'm going to repeat that. The electric field, all the little charges on top of the sphere are all contributing to the measurement of the electric field inside the sphere. And because of Gauss's law, the electric field inside there is 0. Incredible. Right? I mean, assuming Gauss's law is correct, which it is. I mean, as far as we know it. So what about for the distance outside? Let's say we're outside the sphere. What about outside the sphere? What do we do about that? So here's what we're going to do. So for outside the sphere, we already we have the same principle. So we know 4 pi r squared. Little r times the electric field is equal to charge divided by epsilon 0. So therefore the magnitude, therefore we have the electric field, and that is equal to charge, this quantity, newtons per coulomb. And now we can drop a, we know the electric field is a vector, so we can just drop a r roof. And so that's the electric field outside of the sphere. Which this makes sense because this is what we this is kind of what we got with the other stuff. What we got? Well, for a little point, it's very similar, but we have this little extra stuff here because it's a sphere, because surface integrals. So it's like if all the charge, like it's kind of like if all the charge for a sphere was like, if we somehow put it at a single point, we would get quite a similar result. We would get like I'm going to plot it for you. So here's R and here's little r. Here's the electric. That's the intensity of electric field. Maybe I should get okay. Forget about that vector. So that's the intensity of electric field. So it would have nothing, and then it would go up and go down. That's a proportional to the inverse of this. That's supposed to be an R. Yes. So now we have an idea. We have a working idea with electric fields, and we can see electric field. We did the math. We just did the math. The electric field works, and that's important, because the next thing we gotta talk about is that how an electric field gives us the ability to deliver power. So isn't potential difference just one electric potential minus another? Actually, wait, hang on. Before I go on, you have any questions?
Oh, I have so many questions.
Oh, lay it on me.
Why did the electrician spend time with his girlfriend? Because he couldn't resist her.
Aha. Okay. So you got it. Okay, you got it.
Yeah, basically.
Yeah, basically. So like that stuff, like what I simply did is that, I just literally just calculated the electric field inside the sphere, and we know from Gauss's law it's 0 because of how the distribution of the charges on the surface of the sphere. If it were an odd object, or if we drew our loop in a different way, like if we drew a loop to contain some part of the Q, or maybe if Q was only distributed on a certain part of the sphere, well, it wouldn't be 0, which would make sense, because the reason why it's 0 inside is because all the charges are contributing to the influence of the electric field inside, and they're contributing equally, so it would be 0. So in theory, if I got a positive charge inside there, and I move it around, I wouldn't be doing any work. No work, because the electric field's 0. And like, actually, let me show you. So, one might argue that one thing we have to understand is one key component to delivering power to electronics is that we have to know potential difference, because potential difference essentially it creates electric current, not the running water kind of current, but an actual electric current. So you might though say that isn't potential difference just like some V? Isn't it just like some V minus some other V? I don't know, V naught. And there we go. This potential difference, right? There we go, right? No. Because if we think about it in those terms, it's a bunch of nonsense. Like there's like that way doesn't have a physical underlying like phenomena or model that like justifies doing that. Like you're like if I'm just doing it just for the heck of it, it doesn't make any sense. So I remember I said this earlier. I said that circuits is like a specific way of looking at EM theory. EM theory is like the general way of looking at it, but like circuits is like looking at like a specific case of EM theory. So in order to like get to that point for potential difference, we have to show. I'm going to show you how we get to use EM theory to get to that point. And once we get to that point for circuits, we don't have to think about EM theory again, at least until we get to fields and waves, which is not in circuits, so we don't have to worry about that. So, equal potentials. So, equal potentials. We have to briefly go over that, very briefly. The idea of an equal potential is that if a charge moves on an equal potential, the electric potential doesn't change. So, like, if you think okay, I'll show you a little bit about it. Just a very briefly. So you have electric field lines. Actually, hang on. Okay, you know what? Okay, let's say you have like electric field lines. And I don't know, let's say they're going this direction. An equal potential surface could just be that. That's an equal potential. That's an equal potential. That's the idea of an equal potential. Because the amount of force applied on everywhere on this equipotential is the same. Because like these field lines have the same intensity and they're going through it at a perfect orthogonal point. That's an equipotential. If we do
it's like one of those illusions like on the back of like the IHOP menu for kids, like which is the longest? The first one is the longest.
What are you talking about?
Yeah, the first one's the longest. Don't worry. I got it.
The first one is not the longest.
Yeah.
Wait, I don't know what you're talking about.
Don't worry. Go on.
Oh my God. So we go like a little point right here. And field lines are coming out of it. Let's say there's some positive charge. An equipotential would look basically like a sphere. That would be an equipotential. Because the equipotential has to be orthogonal to the field lines. That's the idea of an equipotential. I'm going to give you a little example. Where's my example? There it is. So you know what a Van de Graaff is? Does anyone know what a Van de Graaff is? Hello, anyone?
Yes, it's the thing that people at the salon use or something.
Salon?
Yeah, for cutting their hair or something.
Oh, maybe. So it's like a big metal. It's kind of like what I did in the previous problem, but it's like a real thing. It's like a big metal ball with like charge on it, like ideally distributed evenly. Although that's ideal. So like we want to know. Let's say we have a Van de Graaff, which is essentially the same problem what we did before for electric fields. Let's say right here we have like 10 microcoulomb, a 10 microcoulomb even distributedly charged on the surface of the sphere. This is a sphere. And we have a radius of like 30 centimeters. Let's call that R. So we have point P, just some point P. You're familiar with this. Boom, 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 boom. Little r. So instead of E, electric field, we want to know the electric potential at any point in space. P could be there or P could be inside. Yeah, whatever. You know what it is. So what's the V? What's the potential? Now, you know that okay, so I'm going to do something strange. So hang on. What did I write for? I'm trying to remember. What did I write for electric potential in the past slides? Okay. Well, that's 1. All right. Okay. Okay. I see what I wrote.
You said it was like v minus v0 exactly, and nothing else.
No, not that. I meant like I didn't I did an integral, and I'm like trying to remember what the integral was, but no, I can do it again. So okay, so we know that it's shit. Oh shoot. Trying to remember. Okay. Okay. Joules per coulomb. Work. The work. So how do I do the work? Fs dot ds. Okay. So Vp is equal to so we have the little r go out to from wherever it is, wherever this little r is, whatever the p is. So wherever the distance is from there, because this is how we're modeling the charge, and we're going out to infinity. And f dot dr, s is an f. Oh, this is a weird f. Okay, there we go. And if we divide f by charge, by unit charge, well, then we get electric field. So written another way, we get little r, electric field dot dr. And what was that? Oh yeah, that's what this was. We'd get charge over 4 pi epsilon naught r, whatever the r would be, joules per coulomb. Okay, so I was playing games with you guys. So what if we were on the surface of the Van de Graaff? So basically, if little r equals to big R, we would get about this electric potential. That's 5. So what is this? 30,000 volts. And if we double that, if little r is equal to 60 centimeters, we would get about 150,000 kilovolts. And if little r were equal to 3 meters, we get 30,000 kilovolts. Big volts. And if r went to infinity, well, we would get 0 volts. So the idea of potential difference, well, this is how we measure potential. And I'm going to ask you a question, and I do expect you to know this. What's the potential inside the Van de Graaff?
At the exact center?
No, anywhere inside it.
Anywhere inside it?
Yes.
Well,
you should know this.
It depends how small your step was when you integrated, but I guess it would be 0, right?
Yeah. Do you know why?
Because of page, was it 11 or was it 12?
Yep. Yep. And so that means everywhere inside the Van de Graaff is an equal potential. So now you know what equal potential is. And now you know the relationship between electric potential and electric fields. This is a very important step.
But what does this have to do with like legalism and like laws, like Ohm's law?
Well, one of the things we have to establish is potential by itself. It's like, here's the thing, potential by itself, it's like we're measuring for this kind of is potential difference. What we have here is we're measuring from R to infinity. So, and we calculate that at R at infinity is 0 volts. So if R is equal to big R, the radius on the surface of the Van de Graaff, we know that if we take the potential at that surface and we minus the potential from infinity away, we get a potential difference of 30,000 volts. No, not 30,000, 300,000 volts. Or whatever this, okay, whatever this number is. Whatever this number, okay, hang on. 3, so that 1, 2, 3, 4, 5. 300,000 volts. So 300,000 volts minus the R at infinity, which would be 0 volts. That is a potential difference to a very large distance away. But one thing that's really important in circuits is that we're not doing from our distance infinity away. We're doing it from another point, another reference. So you could say, what about a different potential difference between R and 60 centimeters? Well, that would be minus 150, 150. So potential difference would be that 150,000 volts. But think about that. Think about that. That's like a bigger circle around this. And we're here to talk about circuits. So I need to show you how we can use this electromagnetic theory concept and how does it apply to electric circuits. Like, how can we use this in electric circuits? So this is like an ideal, but in a practicality, we're not dealing with an ideal. Like, maybe you've seen it before, where on circuits we have that little ground zero. Like if I show you, I go back. Let me see if I can find it. So
it wasn't so little 9/11.
So here's the thing. So I'm sure lots of people always add this in the circuits, the ground. I'm sure you've seen this before. So electrical engineers, when they're working with this model, they usually mean this to be like 0 volts. But in actuality, it's not really 0 volts. You know how in your outlet you have power and neutral and ground, earth ground? Earth ground is like closer to 0 volts, and neutral is like this. That's the neutral. And we have a few more steps to go to before we can understand why this works. But and it has to do with equipotentials. Let's see, where the heck was I? Oh, there I was. So physically, So physically, you think a difference in electric potential requires some release of energy. So it's like, if we're going from like one electric potential to another, and like if I get the previous one right here, like think about this field. So we have another equipotential. So if we go from one equipotential to another, well, but the voltage, the influence of electric field on here, this electric potential, and the voltage and the electric field influence on this equipotential is different because they're physically different away from each other. They're physically different. So that engenders a potential difference too. And that's like the reference potential difference. So, But one of the general EM things is that an equipotential is not necessarily an imaginary flat plane in an electric field, because I showed you the Van de Graaff. Like, ideally, the electric field inside of Van de Graaff is 0, and that means there's an equipotential everywhere inside the Van de Graaff. So it's not simply limited to a plane. It's not limited to a plane. It's actually limited to a whole 3D volume for a Van de Graaff. So there's a potential difference between two equipotentials. Equipotentials that are disconnected are by definition different. Unless, well, yeah. I mean, for practical purposes, we're gonna stick with that. There might be some special cases, but we're gonna stick to that. So now, so from the Van de Graaff example, and from the work, you remember the work is integral of fs dot ds, and if divide the fs by q, we get that's electric field, and we get electric potential if we divide it by unit charge. So clearly the electric field is an integral part of understanding this magic fairy pixie dust stuff. And understanding from the Van de Graaff example I just did, moving a charge around, like just because you can move a charge around doesn't mean you're creating a potential difference. Because on here, if you're moving a charge around, that's not on it's not on this plane. If you're moving a charge, not on this plane, but if you move a charge from here to here, well, that's a potential difference. But just because you're moving a charge in space, that's not creating you're not necessarily experiencing a potential difference. So now let's do an illustration from one important idea from classical mechanics. One idea from classical mechanics is, you understand potential energy and kinetic energy. To model potential difference, don't you have to assume or have to see, for kinetic energy, that how energy can be released is by dropping a pin. You can see kinetic energy is released from potential energy. Now, the idea is that that charges, putting charges together, putting charges in different places, that is that is kinetic energy too. You know the idea. I'm going to show you something. So we have an assortment of charges right here. So one important idea is work. The amount of work U versus potential, electric potential. So this is in joules. This is joules per coulomb. So the idea is that this value U, one value where I have to actually put work to move these charges where they are. I have to physically do work to move the charges where they are. And V, think of potential difference, or not potential difference. Think of electric potential is different at any location. Now, if you're close to a positive charge, the potential is very positive. How much potentially, a lot of stored up energy per charge. So how you're moving kinetic energy this, compared to gravity, where it is what influence gravity can have when I drop this pin. It's you understand where it is in space, how much potential energy it has. Now with electric potential, it's if you put like an imaginary test charge, you can see how it will move in this assortment of charges. And that's the idea of electric potential. And you got it. You understand this. I know you do. So we also know, we know like if a test charge is closer to one of the charges, we understand how a test charge will move. Especially from the electric field, we especially can see that more easily. So let's formally call it this. So let's formally do this. So we have point A, point B, we have R, and we have the voltage, but the electric potential at A, and the electric potential at B. And so we know that V of A is equal from A to infinity, E dot dr, and B is from B to infinity, same thing. So we can write it like this. VA minus VB, VAB, boom. That's the formal definition of potential difference. Some people like to write it as VB minus VA and like that. So if electric field, we know if for whatever reason the electric field is 0, the potential difference is 0 because they have the same potential. You can think of that if there's no electric field, like if there's no electric field influencing you as you're moving in an electric field, well, there's no work. No work done. And here's the thing. If you take a different path and you go to the same point, this is still the same. It's still the same. And so if we use some real numbers, say VA is equal to 150 and VB is equal to 50. If we put charge Q, if I have a charge Q in my pocket, like charge Q in my pocket, and I move around, if I want to move to like point B, I have a lot of work I have to do, a lot of physical work. And that work would be the charge. Okay. Work is the unit charge times the electric potential. And that would just be the charge I have in my pocket times 50 joules. Oh, no, not 50. 50. The electric potential is 50, so that we would have joules. And so for A, this is for B. So for A would be that. So if the Q is positive and we're at A, it wants to go to B because B is a lower potential. So so if we were at A and we had charge Q and A is 150 but B is 50, that's a lower potential. The charge wants to go to a lower potential. Like how a pin wants to drop from one space to a lower space, and I have to exert an amount of force to keep it from falling. So it's harder for me to maintain it up here. It's easier if I can go right here. It's the same idea. This is the same idea with positive charge. Now, if it's a negative charge, well, you get the other way. Like they're the same. That's the same thing. It's the same thing. It's just like it's the same thing, but it's like there's an inverse. So if Q were negative, it would want to go the other way. In classical mechanics, it's not, you don't have that, but in EM theory, we have that. So here's the deal. How much energy? How much energy do we have? We have it like this. This is how we write it. And we understand that it would be this. Kinetic energy from, I think, B to A. Or, in my notes, I wrote it like this. Maybe it's the other way around. And this is from the work energy theorem. And so basically Q going from A to B is releasing kinetic energy. It's electric potential becoming kinetic energy. Any questions?
I'm going to say no.
Nice. So you get it.
I didn't say that.
Do you get it?
I can pretend to get it.
But come on. But okay. But I mean, but you see it being illustrated right in front of you, right? But you like you see it happening though, right?
Yeah, I see the scribbles. I see the purple marker, but
yes.
How can I trust the purple marker?
I mean, gosh. Well, you know what? I guess fair enough. So, by the way, a piece of metal is an equipotential as long as there's no charge moving inside of it. And, because inside, as long as there's no electric field inside of a conductor, it's an equipotential. So, these are the physical. This is what the physical concept of potential difference is, and now, there's a connection between electric, and I think you've noticed that you've seen that there's a connection between electric potential and electric fields, because if you take the integral of electric field, you get electric potential. But one of the things is that so you remember, that VP is equal. Yeah, you know that relationship. So what if we let's say that we knew the electric potential everywhere, and how do we find the electric field? How would we find it? Do you know? Say we know this.
You're saying E everywhere?
No, let's say we know, but the electric potential. How will we find the electric field?
Yeah, and ask nicely, beats me.
Come on. Don't think about it. Just brute force. Whenever I run into a problem, I just always brute force it. I like everything, I brute force. So what's the ooga booga way of thinking? Ooga booga, integral, ooga booga, derivative. Yeah, do a derivative. So let's try that. Let's try derivative. So we know from point Q and little q and the distance r, we know that from our past problems, from the past purple ink, we know this, from the before the Van de Graaff. We have, when we did the thing before the Van de Graaff, we have this. That is newtons per coulomb. And we also did the Van de Graaff for for potential. And we have this. So we have this. So if we take the derivative of the voltage, well, let's see what we get. dV dr, we get negative what? Oh, look at that. I've seen that before. It's right there. Oh, there we go. We did it. So if we take the derivative of the electric potential, we get the electric field. Make sure to add our roof. So the electric field, from this point of view, it's like how much electric potential per meter are we're getting. So like right here, like what's the electric potential from here or here or here? So we can write this finally as volts per meter. So now the electrical engineers can get off my back because I'm calling it volts per meter now. All right. So that's the connection between electric potential and potential difference. We got this. We got this by the resistors. So now we can finally formally look at potential difference between two equipotentials, and I'm going to show you how the math works between that. But Matthew, do you understand this? Is this clear? Is there anything that's unclear?
Yeah, I mean, the resolution is great on the video, very clear.
Yes. Okay. How about the math and the concepts?
The math makes sense.
Okay.
I would say, yeah.
But the concepts, how about that? So, like, volts, this like this way of thinking comes from this. dV over dr, distance, meters, volts per meter, electric field is volts per meter. So like electrical engineers think about this in terms of volts per meter, of how far away you're from one part or the other. Now, for circuits, you're not going to see too many electric field problems, but this is the important idea behind it, because we need to induce an electric field in a conductor to invoke current. Like how those warlocks wave their wands and magic happens. This is like the way the magic happens. So 17, potential difference. Ooh, potential difference. Potential difference. I'm gonna write this down. This is so important because potential difference is the heart and soul of electric circuits. The heart and the soul of electric circuits. So let's have an example. say we have two equipotentials. And this is at the X roof direction. And we have, this is the 0, and this is whatever X we have, denote it, whatever. And we have negative charge on plate A, or, well, not plate, equipotential A, sorry, my bad, this is equipotentials. And on equipotential B, we have positive charge, and we have electric fields going this way. If electric fields going this way. So we have, okay, so we have the potential is a function of X for X within like, what is this? This small, is it like what, 20 centimeters? No, 10 centimeters. I think yeah, 10 centimeters. That's a 2. That's supposed to be a 2. And we want to know what's the electric field in this space. What's the electric field? So what we did before, now you can see the math. Electric field is equal to the derivative of the voltage due to the distance. dV dr, with this for this, it's dx. And we know, we all know what derivative is, so it's minus 10 vector, remember, don't forget the vector, volts per meter. So now we found the electric field. And with the electric field, we can calculate the potential difference. So here's how we do it. So we're going to do this, dude. Guys, we're finally going to do it. So we have potential difference. We're going to, the delta V, we're going to call that potential difference. So what is delta V? So from VA minus VB, we have, oh, look at this. We're going to do it. We have A, we have B, we have E dot dx is equal to minus this number from A to B. And we have x roof dot dx, and we know the dot product because we know calculus, and so that's going to be that's just going to be 1. Yeah, it's going to be 1, and we know the integral of 1, right? Yes, we do. It is x. So we got this big old number, x of b minus x of a, and we know x of b is 10 to the minus 2 meters, and x of a is 0. X of a is 0 because we wrote a 0 right there. So x of a is 0, and we get negative 1,000 volts. Now we know potential difference. And so if we do it the other way, if we do VB minus VA, we get 1,000 volts. And that's the idea. Like, if you get like probes and you take it, the probe, like if you get a probe and you get like the positive probe and the negative probe, and you take it from here to here, you're going to get 1,000 volts. But if you like switch it, you get a negative 1,000 volts. It negative. So like this is called the voltage drop. That's the voltage drop between X and 0. And the voltage rise between X and 0 is negative 1,000 because it's not rising, it's dropping. But the voltage drop is 1,000. Now, if we do here, the voltage rise is what was the voltage rise? Oh, the voltage rise is, I think it's 1,000. Okay, I'm getting confused. Forget about that. And a voltage rise is some confusing. It's confusing because you're dropping negatives, too many negatives. Wow. Now we understand voltage, right, Matthew?
I wouldn't say so.
Come on, but I. Oh my gosh! Oh my god! Oh my gosh! Oh my gosh! All right. All right. So, is there another note? I think it was another note I wanted to say. So, with this idea, the electric field is constant, whereas the electric potential varies depending on where you are. That's the idea that I want you to take home. So, as long as there's no charge moving, and we are dealing with solid conductors, the electric field inside a conductor is 0. But because conductors have free electrons to move, and if those electrons seal an electric field, they move to, they're influenced by the electric field. And because they move towards the charges that are emitting the electric field inside would be no more. Because the charges within the conductor have rearranged themselves into having that be eliminated. So finally, we can get to electric current. What do you know about electric current, Matthew?
That it has the letter I.
Yes. Yes. The letter I. Which page was I on? Okay, 19. So we're on page 19. Now we can finally touch electric current. So here's the idea of electric current. Come on, focus. Thank you. So electric current. So say that we have positive charges moving in one direction. That's the same as electric current. And therefore the negative charges are moving in the other direction. And that's because of the way EM theory works. It's like we have positive charges and there's going to be a negative charge to that positive charge. Typically, well, maybe not typically, but in a lot of situations, yes. So now we have the concept of current. Well, I mean the idea of it. But how is that useful? How we have the heart and soul of circuits, but we don't have the body. The body allows us to physically do things. Does it? So think of like the relationship between potential difference and current allows us to access the body to deliver power as like power during a specific amount of time, a time window. Like I said, the potential difference is like the heart and soul of circuits. It is the heart and soul. And it needs a body to deliver power. But wait, we know a relationship still exists. We know that there's a relationship between potential difference and current. We know there is. But like there has to be some sort of physical means of delivering power to power an object, to power a device. And the thing is that you can't just say that this doesn't bring in new variables, because it like this physical means of delivering power brings in some non-linear influences. And we understand there's an advantage for having ideal behavior systems because it's easy to like design for and it's easy to like use and do. Now, it's also easier to help us illustrate design solutions for engineering problems. But the thing is that when we get to reality and get to do a lot of complicated things, do complicated systems through non-ideal situations, we're introducing non-linearity to it, and like this has to affect power delivery. So let's say, what if we consider like total linear relationships between like potential difference and current. And let's say we have potential difference as a function, some constant multiplied by current. So the physical way to get this introduces like issues, which leads to nonlinearity. But is there a way around that? Is there a way? Because like linear systems is easy to like do, and nonlinear systems, oh god, you know how problematic those can be. But before we can talk about the nonlinear systems, we have to have a linear system to base all of our like understanding off, like some ideal mathematical way of doing this. And we can see that we know that power. We want to deliver a power in a certain amount of time, like joules per seconds. So yeah, we have the joules per. Remember, we have the joules per coulomb. Now we're doing the joules per second. So we know that potential energy. We know the potential energy, electrostatic potential energy. So there's the way to model that delivery in a certain amount of time. Wouldn't you think so? Now, the thing is that we can, with a lot of all the not complicated, but with all the math that we did, there is a way to like deliver this stuff. Like we can calculate, like doing integrals and derivatives and other relationships. We can calculate power delivery, but we just need to use other ways to get there. But as you can see, that's annoying, and that introduces issues. And like we're trying to learn circuit theory, and we want to stay away from electromagnetic theory, because like the circuit theory is what we're trying to understand. We're trying to get to be able to do this. If we can like understand circuit theory, we can have simple models or simpler models, and compared to EM theory, because a lot of the methodologies for design, electric circuit design, is basis off circuit theory, but circuit theory itself is based off EM theory. We could use EM theory plus other physics to find the power delivery per second. But it would be really, really easy, or like way convenient, if we could have power joules per second in terms of potential difference and current. That would be so useful. And you're in luck. Surely there's a way to do it, because circuits is a thing. And that thing, le creme la crop. Now we have all the understanding, and now we can finally get to Ohm's law. Now, I know a lot of other people in the course, they would just say, oh, you guys know what voltage is. It's voltage is the derivative of E or whatever. Well, no. It's whatever it is. And you have current, right? So you can find Ohm's law. Ohm's law is easy. Well, here's the thing. Screw that. Ohm's law is not easy. Ohm's law is hard. Ohm's, like, if you to fully understand Ohm's law, you need to know like quantum mechanics. Well, to derive Ohm's law, you need quantum mechanics. And you know what? We're not doing that today. So you're in luck. We're not doing that. So, okay. So I'm going to do a few things very quickly and just sit and watch and like get the large idea. So they say we have copper as a conductor, and let's say we're at room temperature. So we have 300 Kelvin. And we know that the speed of free electrons in copper, V sub E, is really, really big, like a meg. And we know the time between the collisions of the amount of time in between the collisions of the electrons hitting each other. So it's like, the magic pixie fairy dust colliding with each other, and the time between that happening, we have as tau, and that is 3 times 10 to the negative 14 seconds. And the reason why it's so small is because the electrons are really moving fast. And the number of free electrons in copper is copper's cubed, and volume cubed. Oh, that's supposed to be a 3. Volume cubed is about 10 to the 29. So it's a big number because this is it's a unit cubed. It's a big number. So it's like it makes sense because there's like one free electron for like every atom in copper. That's why copper is a good, excellent conductor. And so we know those things, and those things are important to know. So let's say we apply a potential difference over the copper wire, and we know force. We know electric field is the force divided by charge, newtons per coulomb. You remember that. I keep hammering it into you. And okay. Why did I write this so funny? So let's say we have so we know that force is equal to the charge of an electron multiplied by the electric field. Then that E right there is the charge of an electron. Let's keep that simple. And we know acceleration is the force, that force, divided by the mass of an electron. And we know the drift velocity. The drift velocity is what the heck is what did I write for the drift velocity? Okay, so the drift velocity of the electrons moving in that copper can be written in terms of the acceleration times tau. And so therefore we can also write it as the electron charge multiplied by the electric field quantity divided by the mass of the electron times tau. And we know tau. So one thing to note that if the electric field is stronger, the drift velocity goes up, which makes sense because the electrons are moving faster. So if the time between the collisions get larger, then tau goes up. So like they're not colliding as much, and therefore acceleration lasts longer. So acceleration goes up. And let's say we have copper wire. Yeah, wires. Copper wire of 10 meters. So this is equal to the length. And let's say we apply a potential difference of 10 volts. And, okay, so potential difference of 10 volts. And the electric field quantity is 1 volt per meter. So therefore, we have a drift velocity. I already did the math. So it's 1.6 times 10 to the negative 19 multiplied by 3, 10, negative 14, 14 divided by the mass of an electron, which is really small. We're just going to do this. Kilograms. So it's about like 5 times 10 to the negative 3 meters per second. So that's our drift velocity. Now there's a point to this. There's a big point to this. Due to the thermal motion, these free electrons move with 1,000,000 meters per second. But due to the electric field, they only advance along the wire very slowly, like a snail, like the speed of 0.5 centimeter per second. And yeah, it says half. See, it's really small. 5 times 10 to the negative. That's supposed to be a negative 3. That's a negative 3 meters per second. So they are slow. The electrons move extremely slowly, but not necessarily the same thing with charge. Now, for potential difference of V of 10 volts and for a length of 10 meters for the wire, we can look at it another way. So let's say we have a wire and we have an area of the cross section, We have electrons moving this way. And let's say we have a space, and we know current is going this way. We also know the electric field is going this way. The reason why is because voltage is right here. This is the 10 volts. And so this would be the minus part. And we know that the E is equal to the we know E is equal. The reason why we know electric field is because it's the volts divided by the length. Because volts per meter. Electrical engineers volts per meter. So, like, say that in 1 second, the free electrons will move from left to right over a distance, say, of a unit meter. So like 1 meter, let's say 1 meter, yeah. And so if we make like a cross section and calculate how many electrons pass through the cross section in 1 second. So okay, the volume that passes through a length of 1 meter of the cross section VDA, we know the number of electrons per volume, which is N, and E, and we know, so okay, we know charge. So here's how we get it. Here's what I'm trying to do. We can calculate currents. So to get I, we have that cross section of how many the cross section, the volume that passes through one length, 1 meter. Say this could be 1 meter. And as it passes through 1 meter, we also know how many. So like this is we know this is meter cubes and this is meters. And so if we multiply by this and we multiply by the charge, by the charge of an electron, we have current. This is current. Is there, okay. Are you, do you follow?
Yeah, just basically like a flux equation.
Yes. So, but you get it. You get that all this like all this nonsense stuff, like all this stuff right here. You understand that we're getting, what I'm trying to illustrate to you is I'm trying to illustrate that we can calculate the resistance from all of those variables. You're not going to go and you're not going to find out like the current or the number of electrons or electrons going through a certain cross section. You're not finding any of that nonsense out. All I'm trying to show to you is how Ohm's law is generated. I'm not trying to derive Ohm's law. I'm just trying to show you how Ohm's law works, like the idea. So we can write this again as equals to current equals to. Okay, so because like if we take VD, we know V of the drift velocity. If we put this in there in VD and substitute it, we can rewrite current as the charges, because there's a charge right here, so we square it because they're the same number, in tau mass of an electron. What else did I write? I wrote something that was strange. Actually, is that it? Oh yeah, the E. I forgot. E. So this is tau. And the E, because E is right there. So we have E right there. Okay, so this is it. So this is that in amperes. Amperes is the designated SI unit for charge per second, coulombs per second. We call it amperes. Why? Because Ampere did something and we honor him by naming this after him. I think he was French too. A lot of Frenchy guys. So we're going to designate that. Designate this. We're going to designate this as conductivity. So conductivity, sigma, charge squared times n, tau. So one of the things is that the tau is influenced by like the temperature of the substance. So if the heat goes up, well, this goes up too. When the heat goes up, then are they like colliding more? Or times between collision, does it go up or down? Whichever way. So conductivity, we write it as the inverse. No, conductivity, the units for conductivity is Siemens meter. No, Siemens. Okay, Siemens meter -1. And Siemens. This is the Siemens, or whatever, however you say it, Siemens, and that is current per volt. Because well, like I said, yeah, that's how it works out. So to calculate the conductivity for 300 Kelvin for copper, it's about this number. And they're in like one of the things we have to one of the things that we can write that I guess we can write this. The quantity of the electric field is oh yeah conductivity has something to do with electric fields. So we can write this. We can write this because the reason why we can write this is because quantum mechanics. Ooga booga quantum mechanics. So therefore, we can write current. What's this? Current as conductivity times the cross section. This is the cross section area times volts divided by the length. And we can write it, we can rewrite this as volts is equal to the length times the length divided by the conductivity times the cross-sectional area multiplied by I, by current. And this is in volts. And we have Ohm's law. This is Ohm's law. And that is ohms. That's a symbol for ohms. And we just solved all of our problems. So ohms, so the resistance has something to do with the materials you're using to generate current. So from here, this copper wire, we're applying an electric field, which is induced from the voltage, because we can find the electric field. I showed you we can find the electric field from the potential. And we know potential along this wire is changing because potential is a function of distance. I showed you at that equipotential example before. Let me see if okay. So I showed you that this voltage is a function of distance, and it is, because you went from a higher potential to a lower potential. This is like an example, but it does behave that way. So you're going from a higher potential to a lower potential. And the way the current is able to run through this physical material, the combination of all this stuff, all that drift velocity, electrons, number of electrons, and conductivity, all that nonsense, gives us R. And we have Ohm's law. But I think you can see the problem. Do you see the problem, Matthew?
The only problem I see is that purple marker must be exhausted.
Oh, I hope it is. I'm gonna throw it away when it's done. So one of the things that a lot of instructors, they just skip is that Ohm's law, they write it off as a linear, as something that's linear. A linear relationship between like current and voltage. But there's a problem. And I showed you what the problem was. Heat and temperature affect the conductivity. And I think I wrote it down. So, we know, by the way, the resistivity, just very quick, is the inverse of the conductivity. And we can write it as, well, Ohm meters. So we know that the resistance is written as the length over the conductivity times the cross-sectional area, also equivalent to the length times the resistivity. This is resistivity. This is the resistivity. And it is multiplied by the resistivity divided by the cross-sectional area, and this is in ohms. So if the length goes up, if we increase the length of the wire, the resistance goes up. Also, if the cross-sectional area goes up, the resistance goes down. So if we make the wire thicker and big, like big gauge wire, or I guess it would be smaller gauge, or the bigger wire, resistance goes down. But here's the thing: when temperature goes up, resistance goes up too, because of how tau has changed. I'm not gonna. You saw it. You just saw it. So we have ideal circuits, like Ohm's law. Ohm's law, V equals IR. But R is really just a function of temperature, or not time. Like that's temperature. So, like if temperature goes up, tau goes down. If tau goes down, the drift velocity goes down. Because remember, the drift velocity is equal to acceleration times tau. And we also know the conductivity is this. So conductivity goes up, conductivity goes down. Conductivity goes down. So rho goes up, and therefore R goes up. So it depends on temperature. So this is not a completely linear relationship. But for lots of purposes, we're going to treat it as a linear relationship, because we kind of have to for like ideal circuits. So for a certain case basis, sometimes we have to we can't treat it as totally linear. And that is essentially on a case by case basis. Oh boy. So we have so Ohm's law gives us the linear Ohm's law gives us the relationship that we need to find power and to solve all these circuit problems. So as a note, so for different temperatures, like books say you have to adjust resistance. Let's do an example. We're finally going to do a circuits example. So now we have like some sort of power source. And we have what's this? So let's say we have a current meter. We have a current meter, that's a current meter. And we have a resistor. And it's a complete circuit. And the resistor is 50 ohms. And we have current meter. So let's say that we have the voltage goes from 0 the potential difference from plus to minus goes from 0 to 4 volts in a few seconds. So, what does it look like? What does the current meter look like? So if we plot it, we have V, and we have I, and we have 4 over 50. That's 4 over 50 is when eventually the current, when it reaches 4 volts, we will have that comes from Ohm's law, and it'll be a straight line because it's linear. Now, what if if it wasn't linear? If we have resistance of R cold, say R cold is equal to 7 ohms, and R hot is equal to 50 ohms. So therefore, what you would have is something that looks like this. In that case, if like Ohm's law was non-linear, or not totally linear. So another thing, say we have 2 resistors in like something called, we're going to call it series. So we have another example. We have A, resistor 1, resistor 2, and we have B. So R1, R2, and plus, minus. So what's the potential difference between A and B? What is I? So the potential difference between A and B, what is I? And what is the potential difference over R1? So we know the current is going through both resistors. So from Ohm's law, we know the current is equal to R, the resistance, divided by voltage. So what we have here is essentially it's like R1 plus R2 divided by V. And it appears, there you go, that's I. We have I. So we have 2 resistors. You have it's twice the amount of length. Remember from that example, the L? The L, the resistance. Let's see, where is it? Right here. L, just double that. And this is that model. Just 2 resistors, plus them together. So you can see how instead of going through all of this stuff all over again, with doing a simple model of circuits, we can quickly find the information we need without having to do this whole physics stuff. And that's what I wanted to show you. So you can find so if you apply Ohm's law to the first resistor 1. So the voltage, the potential difference for the resistor 1 is just the current. We know the current because we have it right here. So that's the current times R1. Boom, we know it. So we can just substitute this for that, and then we have it. And therefore, we also consequently we also know the potential difference for the resistor for the second resistor. We know that. It's just, instead of multiplying it by R1, multiplying it by R2. Yay! That's the power of Ohm's law if we treat it as a linear relationship, which is what we're going to do. So time for another trick, another circuits problem. By the way, do you have any questions about that circuits problem?
Nope.
So you get it, right?
Yes, I understand how to use the magic.
Yes, now you get it. Yes. So we have two resistors, and this is called, they're in parallel with each other. So, Matthew, what is I? Come on, you can figure this out.
You want an equation for I.
Yeah, an equation.
Yeah, this was like the one over the sum of them or something like that, right?
Yeah. But no, here's the deal. Let me put something, let me give you a freebie. So, we have two currents. So, we have two currents. So, we know the voltage over, the voltage. Okay, so I'm going to ask you a question. We know that the current, the total current, the big current I, what is it in relationship? But what's the simplest relationship you can write for I?
It's negative I1 minus negative I2, all negative.
Negative I1 minus negative I2. That?
Just the sum, dude. Just the sum. That's the sum.
Okay, okay. There. So this is true. That's true. So what is the potential difference between A and B? What's V A B? What is it? Do you know?
VAB. It's this. It's the same as V1 and the same as V2.
Yep. Because if we just know the potential difference across one of the resistors, then it's the same as the other resistor. So it would be I1 times R1, and it's equal to I2 times R2. Boom. Boom. That is Ohm's law, and that's why Ohm's law is useful. Even when it's not, even like that gives us an approximation of how to solve this problem. So, was there anything? Is there anything left? So, with these derivations, we can show that all the stuff is connected. So now, all this crazy magic wizard stuff makes sense. And the things that don't entirely make sense, it's just quantum mechanics. So, oh boy. I wonder if I should tell you. Okay. Do you want to know the magic of how a battery works?
Let's do that in episode 2.
Yeah, that's what I thought. So what I'm gonna do, the magic of the battery is like I would demonstrate why the battery doesn't work. Now let me go back to I'm gonna do this real quick. Now we have the tools to solve this problem, and we're gonna solve this problem, and we're gonna feel amazing. Did I actually solve this problem? So, how do you find R? Well, V equals IR, so R equals V divided by R. I mean I. So, wait, what did I write this down? Are you kidding me? I guess I wrote it down somewhere else. So you know that. So for that problem, you know, equals to VG divided by IG. And that's some number I don't know. So power. How do we find the power of R? This is it. I'm going to show you. This is it. So we have dW, the D charge, times VA, VB, as a function of time. What I just did is a mortal sin, so please forgive me. This is like a mortal sin. I'm probably going to go to hell after doing this. So the work, this is work, which is the charge times the potential difference. And if we do a derivative of the potential difference as a function of time, we get joules per second, which gives us power. What I said earlier, joules per second is the power. So now this dq over dt is coulombs per second, and that is current. So therefore, we have current multiplied by potential difference. So the power is equal to the current multiplied by potential difference. And joules per second, we call it watts. So we can also, to find the power.
Wait. So power is always 4 watts. Interesting.
Watts?
I mean, IV Roman numerals, right? So that makes sense, actually.
4 watts. Yeah, basically. So we can also write, because of Ohm's law, we can write power is equal to I squared R and V squared over R. We can write that. So going back to, no, not that. Wherever I put that.
Okay, so here's the last question. What is the power dissipated by a 1 quadrillion ohm resistor shorting a AA battery?
Oh, 0. Because look at this relationship. If R is really, really big, like big, and this is only like what, a AA battery, so what, 3 volts? Or however it is. Well, the power is very close to 0 watts. There you go.
All right, thanks for my homework help. Thanks.
So, wait. So with this, IG, VG, we know that. So we have R. And if we want to calculate power of R, well, since we know, since we already know it's I squared R, and we know R is equal to VG over IG, so we would have I squared over VG, IG, and we know this is really IG, so it's just IG VG. So that's the power that's consumed by the resistor. Now, I'm going to leave you with one question. What about the power? What's the power produced by the power source?
Produced by the power source?
Yes.
Well, I guess it's just the current of the whole, system that it has to give out times the voltage that it's giving out, right?
Yes. So how would you write it? What's the quantity?
P equals IV or I guess IVG, whatever you call it.
So the answer is that's the magnitude. But I guess to be really nitpicky about it, we got to drop a negative. Because the negative means the power, extract it from the power source. So the resistor is burning this quantity, but the power source is giving out this quantity. So this power. Yeah, so you got it right. You get an A. Congratulations. Yay. Next thing will be, the next thing we got to do is I got to tell you about ideal current sources and ideal voltage sources and non-ideal voltage sources and non-ideal current sources. And I think you already think those are self-explanatory. And the thing after that is Kirchhoff's laws. Those things are very important. We have to know Kirchhoff's laws, but that'll be done later. We're actually we can do a lot of circuit analysis with those tools that I just mentioned, and that will be in the next deal, the next thing. But now you know about Ohm's law, Matthew. You know how the magic works. How do you feel?
Well, I gotta say thanks for explaining all the different kinds of pixie dust. So thank you very much.
All right, cool. All right, guys, that's it. We're done. Good night. Sleep tight. Don't let the bed bugs bite.